So here we are getting to the end of the chapter on logarithms. This is 8.6 on page 702 of your book. We'll call this 8.6a. I don't know if it'll take a B video, but let's just at least call it that. All right, so now we're going to find out what we can actually do with these logarithms in order to make life easier. It seems like we add these new concepts to math that make your life more difficult, but logarithms actually make things easier. And if you remember back in the very first part of this, in 8.3, we talked about how logarithms are exponents, which means as exponents, we can solve some things a lot simpler using logarithms. So for example, if I have a variable in the exponent position there, and I'm supposed to find out what I can take 5 to. 5 times itself, how many times is going to give me 12? Well, I know it's going to be a number between 1 and 2 because 5 to the first is 5 and 5 squared is 25. So it's got to be a number in between there somehow, but what will that number look like? Well, if you remember in your math, it doesn't matter what you do. I can multiply this side and this side by 2. So if you multiply both sides by any number, you have not changed whether or not they're equal. So we're going to do that with logarithms. So I'm going to rewrite this. I'm going to multiply both sides by the logarithm of 5 to the x power, logarithm to the 12. Now you look at that and it's like, oh my gosh, what does that mean? Why did you do that? And how's that going to help me? The way it's going to help is because if you remember in the last lesson, whenever you have an exponent with a log, you can take that exponent and move it over here, which means it's no longer an exponent. And if you'll notice, this x is multiplied by the log of 5. So if I'm trying to find out what x is, I can divide both sides by the log of 5, and that cancels and that cancels. So x equals log of 12 over the log of 5. You get your handy dandy calculator out and you type in the log of 12 and you get 1.0792. Yeah, I just know that off the top of my head. And log of 5 is 0.6990. So divide that out and we get 1.5439. So that is the exponent that we would put in for this x, 5 to that power, that's going to give us 12 for an answer. Okay, so that's all there is to it as far as exponential functions. So let's go ahead and try another one. So we're going to do 25, and we'll put that to the 2x plus 1 power and make that equal to 15. And again, we do the exact same thing. Move this to the front. Okay, so that wasn't too bad. Put these in parentheses. That will save a lot because this is one group that we put in front of the log. So make sure you put that in parentheses. That will help because now I can divide both sides by the log of 25. And those cancel out. And we end up with 2x plus 1 equals the log of 15 over the log of 25, which I don't know off the top of my head, so I will just leave it this way. Okay, next step, we're trying to get rid of everything over on this side except the x. So I'm going to subtract 1 from both sides, and that will get rid of that. Okay, so if I take, let's start solving some of this. Log of 15 over log of 25 would be 1.1761 over 1.3979 minus 1. Okay, so if you divide this out, 2x equals 0.8413 minus 1. So 2x equals negative 0.1587. Divide both sides by 2. And when you divide both sides by 2, you get negative 0.079 for your answer. So again, that number that we just found, if we go all the way back up here to the top, that is the number that would go in here, multiply it by 2, add 1. So 25 to that power is going to be 15. But all they wanted to know was what is x. So that's what we put in here. So let's look at example 2, bottom of page 703. It gives a formula right above that. A equals P. Now this has to do with money. All right, so let's just kind of real briefly go over this. A is the amount of money that you end up with after a certain amount of time. So if you put $1,000 in the bank, it makes so much interest over this many years, and you end up with a final number. That's the number that goes there. This is the amount of money you put in initially. So let's write that so it helps. I'll just write this and then turn the video back on. So if you can read my handwriting, like I say, A is the amount that you have after a certain amount of time at a certain percentage rate. So this is the amount of money you have total after you invested. P is the number you start, is the amount you started with. So $1,000 you started with. This number should be more than this number. Rate, INT, interest rate. N is the number of times per year that it was compounded, which means if every month the bank gives you interest on the amount you put in there, it would be compounded monthly, so it would be 12, because 12 times a year, 12 months in a year. And T is the amount of time you left your money there. Okay, so I'll leave that up there. And example 2 says, how long does it take for $5,000 to double if it is deposited in an account that yields 5% interest compounded once a year? So A, it gives you how much money you're going to have at the end of the time period. It says the amount that you invested is going to double. So we're going to put 10,000 in for A. And it said we started out with 5,000, 1 plus, and then the interest rate, so anything with a percent. In this case, it's 5%. But we have to change 5% to a decimal. You never work with any numbers that have a percent sign. It has to be changed to a decimal. And N, it says it's compounded once per year. So it says number of times it's compounded. So that's just going to be a 1. And then that 1 is going to be up here too. And the, I'm sorry. I said 1 and I put an N. And then the T is what we're looking for. So that's what our equation amounts to. So let's go ahead and go through here. 10,000 equals 5,000 times 1 plus 0.05 to the T power. We don't have to show the 1. So we're going to divide both sides by 5,000. So we get 2 equals 1.05 T. And that's what we want. We want to get it to the point where we can have a single number on both sides, and we can take the logarithm of both sides. So now we're going to go log 2 equals log 1.05, and let's just put that in parentheses. So then we're going to write it as log 2 equals t. Bring that t in front. Divide both sides by the log of 1.05. This goes away. And when we divide that out, we get 14.2 is an answer. So we're looking for t. We're looking for time. So it says that if we invest $5,000 and leave it in there for 14.2 years, the amount of money will double. And that's pretty much what we're doing in that part of the lesson. Let's jump to the change of base part in B as in boy, which is middle of page 704. One of the things that we did earlier is we would have things like the log of 8. And not only did we have something like the log of 8, but we would have the log of 8 of 24. And you can't put that into your calculator, doggone it, because any base on a common logarithm is going to be 10. So it has to be a 10 in order to put that in your calculator. So what this section does is it teaches you how to change every logarithm, no matter what the base, into a log of 10. So here's how it works. We'll use this one as an example. So we've got that. We write it as the log of 10, 24 over log 10 of 8. So this way you can get your calculator out and write the log of 24, log of 8, divide by 2, and you end up getting the answer in base 10. So your calculator can actually do the work for you. So that's pretty much it as far as the change of base formula. So let's look at example 4, which is our last one for this lesson. And it will, let's see if I can move this up. It will just give us a story problem on using logarithms. Suppose that the population in a small city is 32,000 in the beginning of 2010, and that the city council assumes that the population size t years later can be estimated by the equation. Okay, so what they've got, and this works well when it comes to city planning, is you may have a certain population, and you're wondering, should we build this new park? Well, let's use some formula that some math genius comes up with that will give us an idea of how many people will be in our town, maybe like in 10 years, so that we know whether our town grows a lot or whether it just grows a little. So this is the population. So P represents the population, T represents time, E is our natural logarithm that we talked about earlier, so that's the formula there. We don't have to worry about that necessarily. It'll be part of the equation, but it's not a hard part of the equation. Okay, so let's start filling in some of the blanks here. All right, so we're going to put 50,000 here because that's what we want to know. How long it's going to be before our population is 50,000. Because, yes, just under the formula in the book, it says approximately when will the city have a population of 50,000. So that's going to equal okay. Now we're going to divide both sides by 32,000. And that gets rid of that and gets rid of that. So now we have 50,000 divided by 32,000 is 1.5625. And that equals e to the 0.05 t. So notice the t is in the exponent position. And because we're using e, instead of using log, we're going to use ln. But we do it the exact same way. Okay, so then this next step that we're going to do here is we are going to move this in front. and it's no longer an exponent. Divide both sides by ln of e. And if you remember earlier, which you probably don't, I probably wouldn't, we end up with ln of e actually being 1, so that can go away. So now we have this equals this. We divide both sides. Let's get rid of some of this nonsense here that we're not using anymore. Divide both sides by 0.05t, 0.05, and we find t. So we find ln of 1.5625, divide that by 0.05, and that gives t, and that gives me an answer of 8.93 years. So in 8.93 years, our population will go from 32,000 to 50,000. And that's pretty much it for 8.6.